please go ahead sharing your screen, and the presentation will be dealing with how to launch Gaussian without Gauss view in a command line. And then Haley was brave enough to teach us how to scan potential energy surfaces. Okay, floor is yours.
Okay. So I'm going to be talking about how to prepare an input file for Gaussian 9 as a text file instead of using Gauss view and scanning the potential energy surface. So here is what a typical input file looks like for Gaussian. Not including the text box at the top right that says job type and keywords. The first 3 lines with the % symbols before them, these are the link 0 sections. This is the section where you can put in different options for your calculation, but it is optional. So the first line I have here is how to specify how much memory to use. Here I have MEM is equal to 256 megabytes. You can change this, and I think you can also use like KB for kilobytes, GB, like different things like this. The second line is nproc shared. This is how you can specify the number of processors you want to use for the calculation. And then the third line tells the calculation that, or tells Gaussian to save the check file after the end of the calculation, because it does not automatically do this. And then the line after this with the pound symbol before it, this is called the root section. This is where you specify the calculation type and any other options. So here I have HF for Hartree-Fock. And then I have the 321G, just the standard one, I think from Gauss view. And then I have the keyword SP for single point energy calculation. The text box at the top right is where I have keywords for 2 of the calculations we're used to, and then also the calculation I'll show you how to do in a minute called scan. For optimization, it's just OPT, single point energy is just SP, and scan is just scan. So then when you're finished with this root section, you have to leave a blank space between this because this is just the syntax that Gaussian likes to use. And then the next line will be a title section, which is just useful to kind of say what the calculation is. But if you don't want a title, you can just write something generic like title. And then another blank line after this. And then this is where we actually start to describe the molecule that we're looking at. So first I have that line that says 0 and 1. This is charge and multiplicity respectively. So here this is just like a methanol. So it's uncharged, so charge is 0 and it's singlet multiplicity. And then finally the molecule specification, you put in the geometry of the atoms in your molecule. Here I just have it in Cartesian coordinates, but I believe you can also use a Z matrix. And I made this just in the command line, but you can also make your input file using your text editor on your computer, but you want to make sure to save that file as plain text because a lot of text editors automatically save your file with a bunch of formatting included, and that will just mess everything up. Okay. So the next thing that I'm going to be talking about, I tried to figure out on my own, so give me some slack here. But this is the calculation for the potential energy surface of a molecule, assuming that you're changing the length of a bond between 2 atoms. And so I took a little video of myself doing it because I figured it'd be a lot easier than trying to take screenshots of every step. But what you want to do is click the tools button at the top and press this button called redundant coordinates. I already have one there, so I deleted it, and then you'll click add and add a new one. So then here you're going to put in the coordinates for your molecule. I only have 2 atoms, so I'm only putting those ones in. And I'm identifying this as a bond. And then here I'm putting scan coordinate. And I say that I want to take 25 steps of 0.1 angstroms each. And so this is the way my molecule bond length will be moving. So then we just set up a Gaussian calculation like we're used to. looks like it got cut off, but where you specify calculation type, there's one called scan. You'll just press that one and press submit. I'll ask you to save the file. And then once it's done, you can open up the check file. So opening up the check file, you're able to view these results, which is a scan of the total energy as the bond length between the two atoms is increasing. So you can see that as the two hydrogens are getting further and further away from each other, the energy is increasing. And also looks like the first point there is a little bit higher in energy than the second point, which might mean that the two hydrogens are a little bit too close initially, and then that equilibrium bond length might be the second one. And that's it.
Okay, please join me in thanking Haley. I do not hear much applause, but I hope they are on each side. So presentation is open for questions and comments. So if you have questions, please speak up.
I had a question.
Yes, Ola, please.
So the part where you selected the coordinates, where you had 1 and 2, what does the 1 stand for?
So normally it lets you just click on the atom that you want to choose, but it wasn't letting me do that. So I figured because I only have 2 atoms, I would try doing atom 1 and atom 2, and it seemed to work out pretty well. So I think it's just the number of the atom, but I could be wrong about that. Just worked out for me.
All right.
Okay, yeah, thank you.
I have a question. Can I ask?
Oh, yes, please do.
Okay. You showed in the video that when the distance between the atoms was increasing, the total energy was also increasing. Can you just explain this? Like, how is this happening?
That's more chemistry than calculation, but so this is just molecular hydrogen, which is a pretty stable compound. And when you pull the 2 hydrogens apart, they don't like that because it's pretty low in energy for them to be close together. And so you have to put in a decent amount of energy to get them to come further and further apart. And that's why the energy is increasing as the bond distance is increasing.
All right. Thank you.
A little comment to Rizvi, Said Ayun. This calculation is extremely interesting and important for 2 communities. For chemists, if they study reactions, and for all engineers who do force field molecular mechanics, because this scanning of the total energy as function of distance allows to parameterize force fields. So this Gaussian calculation is ab initio, and it gives as a result, these blue dots, the potential energy surface, which can be used later on to run very quick molecular dynamics. Make sense? Yeah, thank you. I think this comment will be also interesting for Wenjian, who is doing this force field. More questions to Haley? I do have a couple. So what should be done to scan excited state potential energy surface?
Use the geometries of the excited state molecule.
But how do, practically to run, which method do you need to specify that it is an excited state? Like in the scanning, it was scan of total energy, assuming that your hydrogen molecule is in a ground state. If you want to do the same thing you did, or everyone did in the other class, how to get the next potential energy surface?
I don't know how to set it up through Gauss view, but I believe you would just do the same thing with the excited ones, and you would take the energy at all the different bond lengths and plot it, right?
There should be an option. There is an option for by using TDDFT, and one can make a constraint that when you deal with excited state and make excited state energy and feed it into the scan. Another thing, can you please show your previous slide? And to those of us who love Ccast, are there any additional comments, or do we need to change anything in the header of this Gaussian input if we want to run it not on a photon but on a Ccast? From the top of your head, do you recall any?
Yes, I believe it uses a PBS scheduler, so you have to add some PBS commands at the top in order for it to be submitted to the scheduler. Okay,
but can we believe that the Gaussian input prepared on in this way on for the photon will work on Ccast as well?
It hasn't worked for me.
Okay, it should, but maybe it needs some adjustments, right?
Okay.
Okay. Last chance to ask questions to Haley. Questions 1, questions 2, questions 3. Let's thank Haley once again. And yeah, thank you for stopping sharing. The next presenter is Lola. Lola, would you please share your screen? And okay, yes, it's good. Okay, so the presentation by Lola is a natural continuation of the presentation by Haley, because Haley was teaching us how to prepare a Gaussian job without graphical facilities, and Lola will tell how to analyze results of the computation. Please go ahead.
Good evening, everyone. I will be speaking about how to analyze the Gaussian output without using Gauss view. Okay, I will just speak briefly about some relevant terms. Total energy is the minimum energy of the system, and SCF is an iterative method that is used to solve for the exact Hamiltonian in the Schrodinger equation. Sort of like allows you to pick an initial geometry, solve the equation, and then checks for the solution till it converges. That's like the solutions from the final step must equal the one with the initial step. So ionization energy is the energy required to remove the most loosely bound electron from an atom. And intuitively for me, I think about it like you can only remove an electron from somewhere that has an electron. So it has to be the occupied orbital. So that's the HOMO energy. Electron affinity is the energy released when an atom is added. You can only add to somewhere that has nothing or doesn't have enough. So basically unoccupied. So that's how I see it as LUMO, like lowest unoccupied molecular energy. And the HOMO-LUMO gap is the energy difference between a molecule's HOMO and LUMO. So here I am showing a video of how I got into my folder. I am looking through my .log file for total energy of my system. And I'll be looking for the line that has SCF done, like I explained earlier. That value right there is the total energy of the system. But if I want to do it through command line, I could just use the grep SCF command, get the name of the .log file, and it will print out the same energy right there. So here I am pointing to the energy of the HOMO and the energy of the LUMO, which is virtual unoccupied. I want to calculate the HOMO-LUMO gap, and I will use BC, which means basic calculator. I will take the energy of the HOMO minus that of the LUMO and get the energy of the HOMO-LUMO. That's the homolumen gap. Yeah. That's all. Thank you.
Oh. Okay, yeah. Please join me in thanking Lola for being a champion in how brief presentation can be. Yeah, thank you. So, any questions to Lola? I have
a question.
Oh, yes,
Oh,
yes,
sorry.
Haley, please. Go ahead.
Can you explain why the total energy is given under the SCF done? What is SCF?
Okay, so like I explained, SCF means self-consistent field. Now, it's a numerical method that is used to solve for the Schrodinger equation. And how it does it is you give it a particular initial guess, which is like how we start with the geometry. You give it an initial guess, it solves the equation, and it keeps doing. And that's why you see it saying after 20 something cycles or whatever cycles, it keeps calculating. Like once you give it the first initial guess and it solves the equation, it gets the solution. It takes that solution and puts it back into the equation, gets the solution. It keeps doing that until it realizes that the last two steps, the solutions are equal. Once they are equal, that's when you say the result has converged. So that's how it does. That's how it does this SCF method.
Haley, are you satisfied?
So is this only found in like an optimization calculation output file or other calculations too?
I think it's usually optimization, but like for any method that requires results to converge, where it has to keep going and going and going, then you would usually find SCF, because it's basically a method. It's not something very specific to like quantum mechanics or anything. It's just a numerical method for solving these equations.
Haley, is it better now or not yet?
I got it. Thanks.
Okay, let me add a comment just for everyone, summarizing. Many thanks for Haley to ask and Lola for answering. It is a little confusion as I can see in the class. So there are two processes that are described in a similar language. So one is finding the ground state total energy for provided positions of ions. So if ions are nailed down and do not move, there is a iterative self-consistent procedure in Hartree-Fock that we did last time in the class and that you submitted as a little homework quizzes. Remember when there were flow chart and things going over and over again until energy converges. So this is what Lola taught us as self-consistent field and where the answer is getting to us. On the top of this, one can do geometry optimization. When upon achieving self-consistent field, one is looking for a gradient in the and modifies positions. And for each new position, one goes in for another SCF cycle and repeats it until the positions are found their optimal interatomic distances. Lola, does it agree with what you were answering?
Yes.
Okay. Haley, is it my words didn't bring any new confuse? Is it reasonable?
Yes.
Okay, yeah, thank you much. Brief comment, Lola, your gap was negative. I think it should be positive. LUMO minus HOMA, not HOMA minus LUMO. Make sense?
Yeah.
Okay. Any more questions to Lola? Questions one, questions two, questions three. Let's thank Lola once again. I hope everyone is applauding, just microphones are muted. And you can stop sharing. So the next presentation is by Rizvi.
Yes.
And I believe basically all talks from now on will be dealing with analyzing further analysis of electronic structure. Basically, what should we do if amount of orbitals is too large and we need to make more detailed analysis? Okay, Rizvi, floor is yours. Please go ahead.
Yeah, can you see my screen?
Yes.
Okay, all right. As Dr. Dimitri has introduced me, my topic is the Perl script to extract the density of states from the .log file, and I will be doing for the closed shell. I will explain the terms, the density of what is the density of states and what is the difference between closed shell and the open shell, and then how we get the log file and what are the Perl scripts. Talking about the density of states, density of states is normally is the proportional of states that can be occupied by the electrons at each energy levels. And if we simply describe the density of state, it is just the distribution of states as a function of energy. And the formula for the density of state is the normal, the easiest formula is it is the dn over d. And this is the one of the basic figure of the density of states, in which we can see that the peaks of energy which are being showed are just telling that we have the energy density of electrons in the peak areas. And we normally know that electrons reside in the conduction band and the valence bands. And this figure is most probably for the metals because the conduction band is higher than the valence band. And we know that electrons are mostly in metals in the conduction band. And then the closed shell. Normally, the shell is the pathway which electrons followed around the nucleus of an atom. And if we speak about the closed shell, then a closed shell is the shell which is completely occupied by the electrons, and electrons will follow the rule of the Pauli exclusion principle, in which state that the only two electrons with opposite spin can be reside in an orbital. And these two electrons can be alpha or beta, or we can say that up spin or the lower spin. Then is the log file. Normally, log file is the output file which is produced when we submit a prepared model of molecules in the Gaussian for calculation. Like in the table, you can see that we normally do the calculation of the for Hartree-Fock or the DFT or any other calculation, and we choose the basis set and the charge value or the spin. And when we submit the file, we receive another command box which contains the .log files. And when we open the .log files, we got this box which tells about the basic properties of the that molecule, like the energy, the total energy of the molecules, or the charge and spin value. We can also open that .log file in the MOBA-XTRM, and which give the very extensive information such as the charge, the multiplicity, the degree of freedom, and ionization energy, electron affinity, and all these values. Then comes the Perl script. Perl is basically, it stands for the practical extraction and the report language. We use this command basically to extract the data which can be in DOS numerical file data, or the other files which contains the energy of unoccupied electrons or energy of occupied orbitals. This is the Perl command which we normally use. And this is basic command, and when we do it for alpha or beta, we will add the alpha in the command line. This is when we put the command and we check the file addition, then we can see these three files are being added. And when we open the when we done with the Perl command, we can do the same for alpha, and this is the output file we received, and it contains a very extensive information like the the step value, the number of steps or the grid index we choose, and in the parameters I choose one, the width instead of 0.1 to just check the what can be the result. So for same we can do for the beta electron, and the same file will be obtained, and then we can just copy the name of this file to another DOS file, because the gunplot normally use the DOS names, and this is the result I obtained by changing the parameters from 0.1 to 1. You can see that the width of the density is very much than the previous one. And this is all from my side. Any questions are welcome.
Okay, please join me in thanking Rizvi. So any questions are welcome. So please, paper is open for discussion. I do not hear questions. I have a question myself. So would you please go one slide back? So are those density of states characterization for the same system?
Yes.
Right?
Yes, yes.
Okay, so what are individual, how to interpret individual peaks on the left? What is their meaning?
Actually, the peaks on the left are for the valence bands, and the up peak is for alpha electrons, and the lower peak is for beta electrons. And it is actually the replica of the alpha into beta or beta into alpha, we can say. On the right side, we have the conduction band.
Okay, so each peak corresponds to one orbital, right?
Yes, yes.
And on the right, there are just a couple of peaks.
Yes.
What happened to them? Where are individual orbitals?
Actually, I was not sure about it, but I just changed the parameters from 0.1 to just to check the like what happened if I change the width of the values, and this is all I got. And
so how do you interpret it?
Sure.
Anyone in the class is very welcome to provide interpretation.
So I think when we change those numbers, so if you just change the number of steps taken in DOS, then you're basically changing the resolution of the orbitals. So so if you choose it like bigger steps, then you will not see as much as details we have in the left graph.
Okay, it's a good idea. And if you have the same number of steps, but let's ask Rizvi which parameter he did change to get the picture on the right.
Yeah, I actually changed the width. I didn't change. Yeah, I didn't change the number of steps. Number of steps was the
so
same.
What's the meaning of width parameter? What does it do to each individual peak?
Yeah.
And did you increase or decrease the width parameter?
I actually increased the width parameter, and
How
it
much?
actually increased from 0.1 to 1. Like I increased it 10 times.
Okay.
Yeah, the step value changed to 10 times bigger.
Very good. Amir, do you have any interpretation based on this additional information? So
Can I try?
Yes, Haley, please try.
Is it like increasing the interval it's looking for the number of states in? So because the interval is so much bigger, all the states come into the same peak?
Yes, almost. Yes, almost everything correct. So all states come to the same peak, but the interval is not changing. We are using the same interval and same spacing of dots. If we are changing width, it means each individual peak becomes broader, and they become so broad that they start to merge together.
Yeah, overlapping.
Make sense?
Yes, yes.
Okay, so once again, making individual peaks broader leads to merger of a peaks. And instead of discrete representation of individual orbitals, we have continuous band.
Yeah.
Right?
Yes,
Okay.
yes, exactly.
Yeah, I think it is really great observation, and thank you for bringing up these figures. It's a really valuable discussion. Any other questions to rizvi? Questions 1, questions 2, questions 3. Let's thank rizvi once again.
Thank you so
You
much,
can-
everyone.
Thank you. You can stop sharing. I think you're still sharing.
I'm trying to clear.
And the next presenter is Anand. Maybe if Anand starts sharing, it will automatically replace
No, I have stopped. Yeah.
the screen. So we all were using GNU plot to generate the figures of the density of states. But what is the mechanic? How the data out of Perl scripts is converted into images. So if you want to modify these images or just change details, we should hear to presentation of Anand and learn new things from him. So Anand, floor is yours.
Yeah. Thank you. Yeah, my topic is draw numerical data with gunpoint software, for example, DOS. So before going to the actual script, just I want to introduce what is gunplot. It is a command-driven interactive function and data plotting program, and it is an open source. And this is the basic interface of gunpoint, what I have downloaded. So this is the console, and okay. So these are some of the graphs. It can be also used as a calculator. If you can see here that simple print 3 plus 8, 11, a is equal to 5. And if you add like a plus 8, it will give you the data. And like exponential and pi, all the data it will give. And sine, cos, all the, it is a very good tool to represent your data. And it is having like, you have to go to your file and like you can create good plots using that gunpoint. Okay, so gunplot is pre-installed in Photon, and it can be simply run by the command gunplot. And you have to create DOS alpha log file or DOS beta log file on your computer, and like it. So in this, the first column is energy, and the second column is the DOS. And now plot the graph using the commands. So this the graph I plotted for like DOS alpha log. So, and this is for beta. And like simply, if you want to like change its width, height, color, and other things, simply you have to type test. It will give you all the, so no need to worry. Like pattern fill, you have to give like 0 to 9 numbers, and like color, there are numbers. Line width, LW, the command is LW, so you have to give it number, so it will give you the different color as well as the width size difference. So I combined both the alpha and the beta DOS, and I got this result. And in the left side, it is balance band, and in the right side it is conduction band, and at the upper side it's alpha, and at the lower side it is showing the beta in the negative sides. So okay, and this I using that Moxa term, and this I am using directly from the gunplot software. So I just change little bit colors by using that test command. It is here, like, so this is all.
Okay, please join me in thanking Anand. Any questions to Anand about this very useful and interesting way to how to modify the way we plot data into graphical information. I do have a question. When we were practicing in a lab, when we were running the GNU plot from a command line, we were not actually entering in the GNU plot environment. We were typing GNU plot and then name of the script, right?
Yeah.
So what is inside the script? If you are not showing it, just tell what do you remember? Like, were there only commands to plot these two lines, or something else? Like how to do scripts to be used by GNU plot?
It is the different commands, like if you want to like plot and like in inverted comma, you have to give that detail of the file, what is there. So
okay, so probably it tells to which file to save the graphical information, right? Okay, and in the command that you are showing now, plot dos alpha dot log and then u1 column 2. So what is this u key? If you select this command that you are showing, the command, the first line on your slide is using MOBX term, and second slide plot dos alpha. Can you navigate your marker to it?
this one.
Yes. Or you have it written in a bigger font on the top of your slide.
Yes,
right
yes.
here. Yes. So you have plot dos alpha u1 column 2. So what is this u1 column 2?
It is like alpha over beta.
Huh? What is 1 divided by 2? What does it mean?
It is alpha over beta.
No.
Okay.
You have two things. First, plot dos alpha, comma, and then dos beta. But in each of them, you have u1 divided by 2.
I think.
So let's go to your.
It is one. One is red color and two is
no.
Sorry.
Let's scroll your slides to the very beginning. Slide number 9. Yeah, this one is good. So your file has several columns, right?
Yeah.
First column and second. So u means using, 1 means X data are taken from column number 1, 2 means Y data are taken from column number 2. So using columns 1 versus 2. Make sense?
Okay. Yeah. Thank you.
Okay. Yeah. Thank you. More questions to Anand? More questions 1, more questions 2, more questions 3. Let's thank Anand once again. And we do have 2 more presentations. So the next one is by Venjan. Venjan, would you please share screen?
Yeah, of course.
Yeah, thank you. Okay, so since we split our talks between 2 days, there we come in and out to different subjects, but Venjan will partially cover what Haley was starting from, but he will focus on the things that we need to deal with if number of electrons is not even. Okay, please go ahead.
Hello everyone. My topic is specify spin multiplicity in Gaussian input. And firstly, let me introduce you some concept about the spin multiplicity. As we all know, there are some properties of electrons like mass, charge, position, energy, linear momentum, orbital angular momentum, and spin. These properties can be classified as intrinsic properties and extrinsic properties. The intrinsic properties, including mass, charge, and spin, these properties cannot be changed or cannot be changed easily. And extrinsic properties is some properties, some variable kind of properties. And for the spin, actually they are the intrinsic angular momentum, or it's a kind of electron movement status. It can be including the spin up and spin down status. So when we do the calculation in Gaussian view, in the method part, we need to choose the method, the basic set, to type the we need to type the charge to choose the spin, and if we choose a proper variable, we can see the variable in the check file. So here, these two numbers, the first one is the charge we type, and the second number is the spin or the multiplicity we choose. Actually, multiplicity is a kind of energy level, or we can understand multiplicity as how many configurations that have the same energy. And in the log file, we also could see some information about different spin, like the alpha for the spin up electrons and beta for the spin down electrons. And we also can see the highest occupied MO and the lowest unoccupied MO in the log file. For the relationship between multiplicity and spin, it could be the equation M equal to double S plus 1, and that's the relationship between multiplicity and spin. How can we understand the relationship in the system of multiplicity equal to M? The system will have the spin S. So that's to see the system consists of M status with spin components from minus S plus 1, minus S plus 2 until S. Such as if we have the system multiplicity is 3, then from the equation S equal to 1, so the components are minus 1, 0, and 1. So after we finish these steps, the next step could be determine the orbital to plot, generate cube file, and plotting the molecular orbitals. So that's all. Please, if you have any questions, please feel free to ask.
Okay, please join me in thanking Wenjian. I really like your explanation of multiplicity, and although you didn't show the equation, you did explain it nicely. So, any questions?
Yeah, I have a question.
Please do, Rizvi.
Can you go back to the slides? Yeah, this one. Can you explain what is the unrestricted here?
Sorry.
Yeah, in the methods, what is unrestricted?
Oh, it's in my opinion, the unrestricted means the electron is free, is not restricted. And yeah.
That's good. That's good. Can you please go forward 1 or 2 slides? Forward, not backwards, forward. Yes, here. So let's look on the orbitals on the left and right that are highlighted with red color.
Yes.
So are they equal or different? Are the numerical values of orbital energies are the same or slightly different?
Yes.
Same or different?
It's different.
Okay, yeah. So, and if we keep comparing energies of orbitals on the left and right, we will observe that they are different. And this is why the word unrestricted is used. So restricted means electrons with opposite spin are taking the same orbital with the same energy. And unrestricted means depending on the spin of electron, the value of orbital's energy can be different. So orbital with the same index can be a little higher or a little lower depending on whether it is alpha or beta. So electrons are not restricted to have the same energy if they're on the same orbital. Up and down electrons, alpha and beta electrons, jumping on the orbital of the same number change the energy of the orbital. So it's orbital energy is not restricted. Make sense?
Yeah. Thank you.
Okay. Yeah. Are there more questions to Wenjan? Questions 1, questions 2, questions 3. Okay, please join me in thanking Wenjan once again.
Thank you.
Okay, and the last but not least is Amir. Amir, would you please share your screen?
Sure. Can you see my screen now?
Not yet. Now we do.
Okay, sounds good.
Okay, I think we are going again to analyzing electronic structure and orbital's energy in a form of density of states, but Amir will focus on the way how these energies and shapes of the peaks are extracted from the Gaussian, right?
Oh, yeah. So it's going to be pretty much like what rizvi presented, but in this case, we are just focusing on the open shell. And yeah, so first of all, Perl command is used to extract information from a file where we're going to extract information from a log file. So we have to have our log file ready, which we are already like generated with Gaussian. And then if you use the Perl command and then you put the address of the script, which Dr. Killen's group already developed, and then you put your file name .log, and then you put 4 numbers after that. And these 4 numbers are the number of steps taken in DOS file, the bandwidth of the DOS, how far below the HOMO to plot, and how far above the LUMO to plot in electron volt. And then with this command, you extract all orbitals. But if you just use the scripts which are specified for alpha and beta orbitals, then you can use it for the spin polarized models as well. So the result of this command will essentially create 4 files for you. The one is DOS_W_B your file name, where B, as I mentioned in the previous slide, is the bandwidth of the DOS. And it will essentially have a file with 4 columns you see on the top. And then the E file name will be a file which has 4 columns here. First one is the number of states, and the second one is the energy in electron volt, then energy in atomic unit, and then the occupation state. And then the other 2 files are, they contain virtual and occupied eigenvalues respectively. And then in order to plot this information, we use the GNU plot, where first of all, you have to copy the file and then name it the dos.log, where this is because the script is written in a way that it just reads the dos.log file. And then you use the GNU plot, where you just use GNU plot, and then you navigate to the direction of the script, and then it will generate the .ps file for you, and then you use the command ps to PDF, right, to like convert the ps file into the PDF. and then you can download it to your local computer. And then if you have extracted the information of the alpha and beta orbitals, then you have to use, first of all, copy each of those extracted. So each of those commands will make these alpha DOS alpha and the DOS beta log files for you. And then you're just gonna rename them to DOS_alpha.log and DOS_beta.log. And then you use the GNU plot, but this time you use the spin version of that. And then that would essentially create this PS file for you. And then you can always convert it to the PDF format and then download it to your local computer, where it will look something like this, which you can see the graph. And then the definition of the DOS. So the formal definition of it is so the DOS of a system describes the proportion of states that are to be occupied by the system at each energy. But the one that helped me to understand it better was the second definition, which says how many energy states exist at a given energy. So you can consider it as like a stadium, as a football stadium, where each row actually, so it tells us how many seats are available at each row, but it doesn't tell us how many seats are actually occupied by people. So in other words, like how many energy states are occupied by electrons. So it wouldn't tell us that. And then, so a high DOS at a specific energy level means that there are many states available for occupation, but on the other hand, a DOS of 0 means that there's no states can be occupied by electrons at that energy level. So that's all I had to present, and thank you.
Okay, please join me in thanking Amir. Any questions? Amir, would you please scroll a couple of slides back? And thank you for analogy with stadium. It's really fun. I never heard it before. One more back. Yes. So this file e_something.log. So
Yes.
by looking on this file only, how can we find which orbitals are occupied and which orbitals are unoccupied? Where is the valence and where is the conduction band?
I think we have to look at the last column, if I'm not wrong. Then can we say that from the last column of the file, which it says 2 or 0?
Yes, exactly. So can you please expand on this?
So so that essentially shows us the occupation state. So if it is 2, I believe it means that there are 2 electrons in that orbital.
Yes.
That's correct. Oh yeah. So when it's 0, it means that that orbital is not occupied by electrons.
That's perfect. That's perfect. I like it very much. Are there more questions to Amir? We will use similar file formats and similar analysis in our next chapter when we will be working with VASP software. So whatever we do will be benefiting our future studies. So more questions to Amir. One more question.
Yes. I have.
Yes, Rizvi, please go ahead.
Actually, it's not a question. It's like a confusion. Can you go back to the first slide, like the one with this one?
Okay.
Actually, we were learned in the class like the 5 parameters, and here as you are showing the 4 of them. So can you it's like not a question, it's just a confusion. Like what will be what was the 5th parameters, and like it was that the how far above the LOMO to plot, it comes under that or something else?
Oh, I thought we used 4 of them, but let me just double check here.
Dr. Dimitri, you can also answer this question, because it's not a question from Amir, basically.
2, 3, 4.
So are you telling that there are more than 4 parameters?
Yeah.
So which is the number 5?
Like in the class, if I remember correctly, it was 2000, 1, 13, and 2, 2. 2000 is the number of steps, and the 0.1 is the width, and the other threes are the one in which I am confused.
Oh, okay. There
Yeah,
was
yeah.
a version of the code that
Yeah,
has
yes,
another number 3, which
yeah.
one needs to give estimate how big is the band gap.
Okay, okay. All right.
Make sense?
Yeah. That's it.
Thank you for bringing it up.
Yeah. Thank you so much for explaining.
Okay. So let's make countdown once again for Amir. More questions 1, more questions 2, more questions 3. Please join me in thanking Amir once again. Many thanks for enthusiastic presentations. I think you are doing really well towards your final grade in this presentation, and thank you in this course. And your presentations are really helpful to everyone in the class. So please join us if your schedule allows for the second session, where we will be more devoted to the graphical part of analyzing Gaussian output. And on Wednesday, we will start new piece of software. I'm not telling that we need to forget everything we learned up to now, but we will switch the gears and try new skills and new software, which will bring us closer to real material world. Okay, many thanks to all presenters. Meeting is done. Everyone is welcome to disconnect, and looking forward to see you tomorrow and on Wednesday.
Thank you.
Thank you.
Yeah, thank you.
Yeah, thank you, Anand.
Yeah, thank you for the inputs actually. Yeah.
Yep. Thank you for adjusting on a short notice and making these changes. I think it's really important for everyone in the class.
Yeah. Thank you. Bye-bye.
Bye-bye.